In this video, I'm going to show you how to modify the dump1090 software to capture some characteristics of the received ADSB signals. Now, the motivation for doing this is that we want to perform spoofing detection, and to do so, we need to observe some features of the received signals, whether that's the signal power or say some of the data that's actually inside the messages, such as latitude and longitudes, airspeeds, things like this. And in fact, a sophisticated spoofing detection algorithm will take into account as many signal features as possible. Say, for instance, some sort of machine learning approach that could contain many features. But for now, what we're going to do is we're going to focus on modifying the dump1090 software to extract one single feature, and that is the received signal power for the messages. And so we're going to do that inside the new radio virtual machine that we set up in previous videos, and I'm assuming that you've gone through those and you have the dump1090 software installed. So we're going to be doing some C programming, so we need to get set up to do that. So go ahead and open a terminal, open Terminator, and then cd into your dump1090 directory, and then type ls and press enter. And what this is showing is the contents of the dump1090 directory. And so the way dump1090 is structured is almost all of the implementation is contained in this one file, which is dump1090.c. And so that's what we're going to be modifying. So of course, to do C programming, or any programming for that matter, we need some sort of editor. And so there's lots of different options you can use for editors. The virtual machine comes pre-installed with Visual Studio Code, so you're welcome to use that if you like. For this demonstration, I'm going to use a very simple editor, which is just gedit, which is a text editor that comes with many Linux distributions. And so we want to open this dump1090c file in gedit, so go ahead and type gedit space dump1090.c, and then at the end of this line, insert an ampersand like that. And all that's going to do is, once we launch gedit, it's going to return control of the terminal to us so we can use the terminal for other things. So go ahead and press enter. And so this is the contents of dump1090.c. Go ahead and scroll to the top of the file. So the gedit editor will put line numbers for the lines over here on the left side of the window. And that's going to be useful because I'm going to refer to different parts of the code, mostly by line number. So let's kind of take a step back and take a broad look at the code. So go ahead and scroll all the way to the bottom of this file, and we can see that the code is about 2,600 lines long. There's lots and lots of functionality inside it to do things like signal detection and decoding of the ADSB messages. But what we're going to do is we're going to focus on one very specific section of the code, and that's the section that is basically looking at the raw received signal samples from our RTL SDR dongle and attempting to detect an ADSB message. So that functionality, almost all of it, is performed in one specific function in this file called detect mode S, which is, so go ahead and scroll up to line about 1300. So specifically, it's on line 1324 here. This is the function that we're going to be concerned with primarily. And this function, as the name implies, it detects a mode S. And by the way, mode S is the structure. It basically refers to the structure of the message that the ADSB signals use. This function takes in those RTL SDR samples and then attempts to detect a message. And one important thing to note here is that the input to this function is a array. That's what this M pointer is. This is an array of magnitudes of the samples received by the RTL SDR dongle, and we're going to basically be performing operations on this to compute signal powers. So there are, several steps here in this function to detect an ADS-B signal. We're going to sort of ignore most of them and focus on one specific part, which is once we've successfully detected a message rather, we then want to compute the power of it and then output that power in a way that we can sort of process it. So scroll down to about line 1500. And look at line 1529. It's an if statement, if mm.crcok. All this is really saying is that the message, it contains a cyclic redundancy check, which is a way to sort of verify that the message is correct. And this statement is saying, well, if that CRC is okay, then we'll proceed with other things. And in our case, other things is going to be computing signal power. So once we've reached this point in the code, we know that we have a ADS-B message detected. So go ahead and insert a new line after the if statement. And first thing we're going to do is compute the message power. So we're going to use a variable to store that power value. So type double PWR, that's just creating a new variable called power, and equals 0. We're going to initialize it to a value of 0. And this is C programming, so we need to terminate our lines with a semicolon. So we had to put a semicolon there. And then give yourself a new line. And then we're going to write a for loop that loops over that sample array that I mentioned before and basically accumulates the values of it. So type for and then open close parentheses and then go back to the body of your parentheses. And we need an iterator. I'm just going to call it int II. We're going to start at value 0, so equals 0, then a semicolon. And we need to know how many samples to look at. Basically, we're going to look at the total number of samples that are required to encode an entire message. And that value is stored in a variable called mode s, all uppercase, underscore long, underscore message, MSG, underscore bits. So go back to the beginning of this word and type II less than because we want to, this is basically our termination value. And then go back to the end of this mode S word and then times 2. And then enter another semicolon and then II plus plus. So this is what the first line of the for loop should look like. I'll highlight it for a second. And then give yourself a new line and then indent a few spaces. And we want to accumulate values from that sample array. So we'll say PWR plus equals because we want to accumulate. And then M, which is the name of the array. And then give yourself a square bracket open, square bracket close, and a semicolon. And then go back to the body of your square bracket and type J plus II. And this is basically what this is going to do is accumulate the values of those samples for the received message. So we want to sort of normalize that accumulated value by the length, by the number of samples. So give yourself a new line and enter PWR / equals. In other words, divide this value. Mode S underscore long underscore message underscore bits times 2 and then semicolon. So, at the end of these operations, this PWR is going to contain the sort of the power of the message. So now that we've computed that, we need to store it somewhere that we can actually do things with it because right now it's just kind of in a variable. So what we're going to do is drop that value out to a file. And we want to, along with that power, we also want to output the latitude and the longitude from the received message. So in other words, we're going to, compute the signal power, and then we also want to see what the latitude and we know where the aircraft was located um, when it was broadcasting this message. And so if we want to get the latitude and longitude, we're going to have to introduce another variable and do a bit of processing. So go ahead and type struct aircraft and then star a, which is creating the variable a, which is an instance of this aircraft struct, which is defined earlier in the file, and then say equals interactive receive data, just like that. And remember, this is C, so everything's case sensitive. So you'll need an uppercase R and an uppercase D, and then open close parentheses, and then inside say ampersand MM, and terminate with a semicolon. And then give yourself a new line. And we're going to write an if statement. So if, open close parentheses, and then a dash right angle bracket position computed equals 1. So one thing to point out is that some ADSB messages do not contain latitude and longitude information, but we only want to look at the ones that do. And so we're going to introduce a flag, which is named position computed, which indicates in this aircraft struct that, hey, we actually do have a latitude and a longitude available to look at. So we're just going to use this as a flag to know what data to capture. So go to the end of this if statement line and give yourself an open curly brace, and then a new line and a closed curly brace. And then inside the body, in between these two braces, we're going to basically insert the code to drop out our data to a file. So enter fprintf, open close parentheses, semicolon, and then come back to your body, and then type power log file like this with a capital L and capital F, comma, and then two double quotes, and then inside the double quotes say %f, 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 and then \n. And what this is saying is we're going to capture 3 floating point values and then insert a new line. And so what those values are going to be is, after your double quote, give yourself a comma, and then the first thing we're going to log is that power value we computed, so PWR, then another comma, and then the latitude, which you do by entering a dash right brace or right bracket, angle bracket, and then lat, and then give yourself another comma, and then say a dash right angle bracket lon, which is for longitude. So what this line is doing is it's dumping out to the power log file every a power, a latitude, and a longitude on a single line. And now give yourself another new line after the fprintf and type f flush, open close parenthesis, semicolon, power log file. And all what this is doing is ensuring that the data that we're logging to a file actually gets logged to a file after we execute this fprintf. So this is all the new code that we need to introduce into the detect mode S function, but we need to make some changes in other parts of the code to allow this to work. And so the first thing we're going to do is we're going to introduce this position computed flag into this aircraft struct. So to do that, you want to scroll all the way to the top of this file up to line 1, and then slowly start scrolling down until you see a struct like this, struct aircraft. So we want to introduce a new member variable into the struct. So give yourself inside the struct a new line and say int position computed like that with a capital C. So that's just introducing that variable into the struct. And now inside the actual processing code, we need to update this flag. And so go down to approximately line 1800 specifically line 18 around 1815. We're looking for this block of statements that has a comment on it if the two, starting with the if the two data. Basically this if statement here. This decode CPR function is what's actually computing the latitude and longitude. So if we reach this point in the code, we know that we have latitudes and longitudes. So we're going to insert a new line after that function and say a dash angle bracket position computed equals 1 and then semicolon. And then we need to initialize this position computed flag with a 0 value somewhere, and turns out we can do it right above the if statement. So give yourself a new line after the if statement, and then a dash right angle position computed equals 0. So that's just updating that flag so that we know when we have a valid latitude and longitude value. Okay, so the last thing we need to do is set up basically the variables that control that file that we're writing to. So scroll all the way up to the top of the source file one more time, and then scroll down until you see some statements with pound define, and scroll to the end of those. So after the last pound define here, after approximately line 94, give yourself a new line, and then enter capital file and then star power capital L log capital F file. So that's just creating it. We're creating a global variable that's going to be a reference, a pointer to the file that we're going to write to. So now that we have that pointer defined, we need to actually open the file inside the code at an appropriate point in the code, and we're going to do that in the main function. So go ahead and scroll down to line about 2600. I know we're kind of jumping around a lot. And we're looking for, okay, it's going to be around 2630. What we're looking for is a block of code like this. It has while one. This is sort of the main processing loop, one of the main processing loops for the code. And all this is doing is this is a loop that reads samples off of our RTL-SDR dongle and then does some processing on them and then feeds them into the detect mode S method that we were looking at before to do detection. The program, once it's executing, is going to stay inside this while loop until we break out of it by pressing Control C. So it's logical that we want to open the file before we enter this loop. So give yourself a new line above the while one statement here and enter power log file like that equals F open, which is opening the file. Give yourself an open close parenthesis and semicolon, and then come back to the body, and we're going to enter a name for this file. So give yourself 2 double quotes, and the file name, which we'll call it message powers.log. And then after the last double quote, give yourself a comma, and then 2 more double quotes, and then W. That's just saying when we open this file, we want to delete all the contents of it when we open and start fresh. So this is what the fopen line should look like. I'll leave that there for a second. Now we will close the file after the user presses Control C and breaks out of this while loop. So directly after the curly brace for this while loop, which is here, give yourself a new line and say F close, open close parenthesis, and then the name of the pointer to the file, which is power log file, just like that. Okay, so at this point, we should be logging signal powers to a file. So let's go ahead and test it. Go ahead and say, click on save up here in the upper right hand corner, and then come back over to your terminal. And to compile this code, we have a make file. So just type make. Now, if there are no errors in the code, it should just build. But if there are, it'll come back and tell me. So let's see if I have any bugs in the code. That's a miracle. Got it right the first time. Okay. So now that we have compiled our new functionality, we're going to test it by running dump1090 and then seeing if we get our values dumped out to a file. So go ahead and type period / dump1090 and then -- interactive and then press enter. And at this time of day, it just so happens that there's a lot of air traffic going on in my area. So that means we should get a lot of data really quickly. I'm going to let this run for, 30 seconds or so, and then press Control C to stop the program. Now, let's see if our our log file got created. So type ls and press enter. And we see we have this new file called messagepowers.log. So let's take a look inside that file. And one way to do that is to use the cat command if we just want to very quickly look at the file contents. So type cat space messagepowers.log and press enter. And we look at the contents of this. So the first column is a power value. Looks to be reasonable. The next is a latitude value, and the next is a longitude value. So these all look pretty reasonable values. Okay, so now we've got some data out of our receiver. So let's do just a little bit of analysis on this data to see what it looks like. And what we're going to do is we're going to create a scatter plot of this data. We're going to use these latitude and longitude values to sort of compute the distance, or at least a value that's kind of proportional to the distance from our receiver. And the way we're going to do that is to use a program called Octave, which if you're familiar with MATLAB, it's basically a clone of MATLAB, but it's free. So you might need to install that. So to install it, type sudo apt install Octave and press enter. Now I've installed it already, so this step really isn't going to do anything for me, but on your end you might have to wait for this installation to finish, so you would enter it like that. Like I said, I've already got it installed, but go ahead and run this and install Octave if you don't have it already. So once it's installed, we need to launch it. So type Octave space -- GUI. That's just going to give us a GUI to work with, and then press enter. And this is the kind of the main Octave window. This double right bracket is our command prompt where we're going to type our commands. I'm going to grab these sort of windows on the left, this workspace and file browser windows, and sort of make this a little bit smaller just so we have a larger command window. And so what we're going to do is load the data from our log file and scatter plot it. So to do that, enter data file equals fopen and then open close parentheses, and then the name of the log file, which was messagepowers.log, then press enter. So this data file variable is now essentially a handle to our data, so we can use it to read in the data values. So we're going to use a program called, or excuse me, a function called text scan to do that. And so to invoke that, enter my data equals text scan, open close parentheses, and then the first argument to this is our data file handle. So just type data file like that, and then comma, and then we need to tell the text scan function what our data looks like. And the way we do that is enter two double quotes, and every line that it reads, we want it to know that it's 3 floating point values. So we say %f, 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 just like that. And then I'll leave that up for a second, and then go ahead and press enter. And it looks like we can kind of tell already that our data got loaded correctly. So we now have this new variable, my data, which is a cell variable. If we say size my data, it's 1 row by 3 column. Each one of these columns is represents one of the columns from our data file. So if we say my data curly open curly close 1, This is going to give us all of our power values. And then if we do 2, it's going to give us our latitudes, and then 3 give us our longitudes. So let's assign that data some friendlier names. So let's say powers equals my data, then open curly 1 close curly, like that. It's just assigning those values to the variable powers. And then we'll do the same thing with the latitude. So lat equals my data, open curly close curly 2, like this. And then longs equals my data, open curly 3, like that. So now we've just got those data with 3 sort of friendly named variables. So now let's compute the distance from our receiver to the latitudes and longitudes that our messages contain. So to do that, I need to know where the receiver is roughly in latitude and longitude. And the way I'm going to do that is launch Firefox and then go to Google Maps, just type Google Maps or something. And in my case, it's kind of centering me roughly over where I'm located. I don't have to be too precise with this. I just have to be close to where I am. Now in Google Maps, if you right click inside the map somewhere, it will give you a latitude and a longitude value for that point. So go ahead and left click on that value. What that'll do is copy those values to your clipboard and come back over to your octave window here, which is this blue circle, and right click and paste. And so we're going to assign these values to variables. So take your cursor over to the beginning of the line and say my lat equals this. Then get rid of that comma and replace it with a semicolon. And then say my long equals this. And then press enter. So now we have roughly my latitude and longitude, which is the latitude and longitude of our receiver. So if you want to compute the distance, sort of the actual distance between 2 points, which are given by latitude and longitude, there are exact ways to do that. Sort of involves computing, the distance you travel over a sphere. There are formulas for this. I'm not going to use the exact formula for that, for at least for the purpose of this demonstration, just because I want to keep it kind of simple. So I'm going to compute the Euclidean distance between all these different latitudes and longitudes in my position, which is, not an exact measure of distance, but it's just something that's kind of proportional to it. So type dis equals, and then SQRT, which means square root, open close parenthesis, come inside this, do another set of open and close parentheses, and inside this inner parenthesis, type my lat minus lats, which is just taking the difference between my position and all those other positions. And then after the inner right parenthesis, type period caret 2. That's just computing the square of those values. Then type plus and another open close parentheses. Then inside that type my lon minus lons. And likewise, after the quantity, do period caret 2. I'll leave this up for just a second so you can type it in. And then when you're ready, press enter. Oop. I guess I made it my long, excuse me. Leave that up for a second. And press enter. Okay. So these are values that are not the actual distance, but they're just kind of proportional to distance, which for what we're doing is fine. So now we just want to plot all of this stuff. So we're going to use a scatter plot. So type scatter, and the x-axis is going to be those distances we computed. So say dis, comma, and then the powers. So PWRS, and then close parentheses, and then press enter. And go ahead and maximize this window. And so, yeah, this is a plot. Basically, this is a plot on the x-axis. This is a value that's proportional to distance, and the y-axis is a value that's proportional to the received signal power. And as you can see, at any particular distance, we have a wide range of received signal powers, but we do see that there is a trend as distance increases that the sort of the maximum received power definitely is decreasing. You can see it's almost like a parabolic shape. Um, so we're going to kind of use this observation in future videos to come up with kind of an algorithm or an approach to identify spoofers. But for now, just kind of, you know, note that these values that these distances and powers are kind of telling a story that, as we would expect, is the aircraft is farther away, the average power that we receive from it is lower. So yeah, that is sort of a kind of a long explanation of how to compute, basically extract a signal feature and do just a little bit of data processing on it. So if you've stuck with me through this whole way, thanks for watching, and I will see you in the next video.